What if everything we see around us, every star, every galaxy, even the fabric of space itself, began with a single, impossible leap? Not a fiery explosion or a slow cosmic unfolding, but a sudden, inexplicable jump from nothingness to existence. This is the mind-bending possibility at the heart of quantum tunneling, one of the most mysterious phenomena in the universe. Picture a universe so young it hadn't even begun, a void where the rules of physics as we know them didn't apply yet. And then, in a fleeting instant, something unimaginable happened. Particles appeared where they shouldn't have, energy emerged from nowhere, and the cosmos took its first breath. This isn't science fiction, it's a real theory that challenges everything we thought we knew about how the universe began. Quantum tunneling defies logic. In our everyday world, if you throw a ball at a wall, it bounces back. But in the quantum realm, particles can sometimes pass straight through barriers as if they weren't even there. It's like walking through a locked door without opening it, a feat that seems impossible, yet it happens constantly on the tiniest scales. Now, imagine applying that same bizarre principle to the birth of the universe itself. What if the entire cosmos emerged because of a quantum tunneling event, a cosmic loophole that allowed existence to spring from nothing? The implications are staggering. It would mean our universe didn't just appear out of nowhere, it tunneled into being, slipping through a crack in the fabric of reality. This idea isn't just wild speculation. Some of the brightest minds in physics have explored it, weaving together quantum mechanics and cosmology to ask, could tunneling be the missing piece in the puzzle of our origins? Today, we're diving deep into 30 groundbreaking theories that explore this very question. From the earliest moments of creation to the mind-bending physics that might explain it all, we'll uncover how quantum tunneling could rewrite the story of our universe. Whether you're a science enthusiast or just someone who loves a good cosmic mystery, this journey will stretch your imagination to its limits. So buckle up, we're about to explore the universe's greatest what-if and uncover the secrets hidden in the very first quantum leap of all time. To understand how the universe could have tunneled into existence, we need to rewind to a time before time, a state of pure, unfathomable nothingness. But here's the twist, even in the absolute void, quantum mechanics tells us nothing isn't truly empty. At the tiniest scales, space fizzes with fleeting bursts of energy, particles popping in and out of existence like bubbles in a cosmic soda. These are quantum fluctuations, and they might hold the key to our universe's birth. Imagine a vast, dark ocean where waves suddenly rise and vanish without warning. That's the restless energy of the quantum vacuum. Now, according to Heisenberg's uncertainty principle, even nothingness can't sit perfectly still. Energy and time are locked in a strange dance. The more precisely you measure one, the less you can know about the other. This means empty space can't have zero energy indefinitely. Tiny, unpredictable bursts borrowing energy from nowhere just for an instant are constantly happening. Most vanish as quickly as they appear, but what if one didn't? What if a quantum fluctuation didn't just fizzle out but tunneled through an energy barrier, transforming into something far bigger? That's where zero-point energy comes in. Even at absolute zero, the coldest possible temperature, the universe still hums with residual energy. It's like a car engine that never fully turns off, always idling, always ready. Some theories suggest this underlying buzz could have provided just enough push for a quantum fluctuation to break free, triggering a runaway expansion we now call cosmic inflation. One moment there's nothing, the next, a microscopic blip of energy tunnels through an impossible barrier, unfurling into an entire universe faster than the blink of an eye. Think of it like a snowball tumbling down a hill, growing exponentially as it rolls. But here, the hill doesn't exist yet, the snowball creates it as it falls. That's the surreal beauty of this idea. the universe may have forged its own birth, tunneling from a fleeting ripple in the void to a roaring cascade of spacetime. This isn't just poetic equations in quantum field theory and cosmology suggest it's plausible. And if true, it means our entire reality could trace back to a single, unrepeatable quantum accident, a cosmic stroke of luck written into the fabric of physics itself. So the next time you look up at the night sky, consider this: every star, every galaxy might owe its existence to a microscopic hiccup in nothingness, a jump so improbable it only had to happen once. But what if our universe's birth wasn't a solitary event, but a cosmic collision, a shattering impact between two worlds we can't even see? Enter the multiverse collision theory, where quantum tunneling might have been the bridge between dimensions. Imagine two sheets of paper floating parallel to each other in a dark room. Normally, they'd never touch, but if those sheets were vibrating, stretching, or warping through higher dimensions we can't perceive, they might suddenly slam together with enough force to ignite an entire universe. This isn't just fantasy, it's rooted in string theory's most ambitious ideas. In this framework, our reality isn't the only one. Instead, it could be one of countless branes, short for membranes, vast, fluttering surfaces drifting through a hidden multidimensional space. According to the ekpyrotic model, our universe began when two of these branes smashed together like symbols in the dark. The energy of that collision didn't just create matter and light. It might have been funneled through a quantum tunnel, a fleeting loophole in the rules of physics that allowed existence to spill from one dimension to another. Think of it like lightning jumping between clouds. The charge builds until flash. It forges a path where none existed before. Quantum tunneling could have acted the same way, providing the spark that transformed a higher dimensional collision into our reality. The math behind this is staggering. Calculations suggest these colliding branes would stretch and compress spacetime itself, generating fluctuations that eventually became galaxies, stars, and planets. And here's the wildest part: if this model is correct, it could mean the Big Bang wasn't the absolute beginning, but just a violent chapter in an endless cycle of collisions. Critics argue we'll never detect these other branes directly. They could be forever out of reach in dimensions folded smaller than atoms. But supporters point to subtle clues, like faint patterns in the cosmic microwave background, that might bear the scars of that primordial crash. Whether this theory holds up or not, it forces us to ask an even bigger question. What if our universe isn't the universe, but just one ripple in an infinite ocean of realities, all connected by quantum leaps we're only beginning to imagine? One of the most unsettling possibilities in modern physics is that our universe might be sitting on a cosmic knife's edge, not in a true state of stability, but in a precarious almost that could collapse at any moment. This is the heart of false vacuum decay, a theory suggesting our entire reality might have begun when an unstable quantum field took a catastrophic tumble into a lower energy state. Picture a marble resting at the top of a hill, balanced so perfectly it seems stable, but give it the slightest nudge and it comes crashing down. Now imagine that hill is the very fabric of space-time, and that marble is the Higgs field, the invisible quantum energy that gives particles their mass. According to this theory, the universe didn't start with a bang, it started with a slip. In quantum field theory, vacuum states aren't empty. They're brimming with latent energy, like a coiled spring waiting to snap. A false vacuum is a temporary high-energy state, a cosmic illusion of stability that could collapse into a more stable, lower-energy, true vacuum. The terrifying beauty of this idea. That collapse could happen via quantum tunneling. One tiny region of space, through sheer quantum randomness, might tunnel through an energy barrier and trigger a cascading phase transition. A wave of true vacuum spreading at the speed of light, rewriting the laws of physics as it goes. And if this happened once before, it could explain the universe's birth. Here's where it gets eerie. The Higgs field, discovered in 2012, behaves suspiciously like it's in a false vacuum state. just slightly too energetic to be truly stable. Some calculations suggest it might be teetering on the brink, waiting for a quantum nudge to decay. If true, this means the universe we know could be a fleeting bubble in an unstable sea of higher energy vacuum, and another tunneling event could erase it in an instant. But it also points backward. What if our universe was born when a previous false vacuum somewhere else decayed, releasing a firestorm of energy that inflated into everything we see? The math behind this is both elegant and haunting. When a false vacuum decays, it doesn't just release energy, it redefines reality. Particles could gain or lose mass, forces might change strength, even the speed of light could shift. In that sense, our universe's laws aren't necessarily fundamental. They're just the local bylaws of this particular vacuum bubble, and if other regions decayed differently, they could harbor alien physics we can't begin to fathom. For all its existential dread, false vacuum decay offers a tantalizing clue about origins. If the Higgs field really is metastable, then quantum tunneling didn't just create the universe, it set the stage for every atom, every star, every life form to exist under rules written by that first, irreversible fall from grace. The cosmos might not be a one-time accident, but a single flicker in an endless cycle of collapses and rebirths, each tunneling event spinning off new realities with entirely different destinies. So next time you hear about the Higgs boson, remember, the so-called God particle might be less a creator and more a cosmic tightrope walker, dancing on a thread between existence and oblivion. What if our universe wasn't born from nothing, but from the belly of a black hole in another reality? This is the spine-tingling premise of Lee Smolens's Fecund Universes theory, where cosmic birth isn't a one-time event, but an endless cycle of black holes spawning new realities like seeds scattered across the multiverse. Picture a black hole singularity, a point where gravity crushes matter into infinite density, where space-time itself warps beyond recognition. In our universe, nothing escapes a singularity's grip, not even light. But quantum mechanics doesn't play by those rules. Deep in that chaotic core, particles can tunnel through barriers that should be impassable, flickering in and out of existence like glimpses through a cracked door. Now imagine one of those quantum tunnels didn't just let a particle escape. It became an escape route for an entire universe. According to Smolens's radical idea, when a black hole forms in a parent cosmos, its singularity might undergo a quantum tunneling event so extreme it flips inside out, exploding not into the same universe but into a brand new spacetime. Like a cosmic Russian nesting doll, our universe could be the hidden offspring of a black hole's violent death in another reality. The math behind this is dizzying. Calculations suggest the extreme conditions inside a singularity could warp quantum fields so intensely they trigger a new inflationary expansion, a big bang from a black hole's ashes. This isn't just poetic speculation. Black holes already bend the rules of physics in ways that mirror the early universe's conditions. Both feature unimaginable densities, temperatures, and energies, so similar that some physicists argue the Big Bang might have been a singularity in reverse. And here's where it gets even wilder. If each black hole births a new universe with slightly tweaked physical constants, cosmic evolution itself could favor universes that produce more black holes. Over countless generations, universes would reproduce, their laws fine-tuned by a kind of cosmological natural selection. Critics argue we can't observe these parent universes, they're sealed off behind one-way event horizons. But supporters counter with eerie clues. If our universe emerged from a black hole, its initial conditions might carry faint echoes of that violent transition. Some even suggest anomalies in the cosmic microwave background could be scars from that primordial tunneling event. Whether Smolens's theory holds up or not, it forces us to reconsider black holes not as cosmic dead ends but as potential portals, dark wombs where new realities take their first breath. So the next time you hear about a distant black hole devouring a star, ask yourself, Could its collapse be the first cry of a universe we'll never see? What if our universe isn't truly three-dimensional at all, but a vast, shimmering hologram, a cosmic projection flickering into existence from a two-dimensional boundary we can't perceive? This is the mind-bending premise of the holographic principle, a radical theory suggesting reality as we know it might have emerged from a quantum tunneling event on an unimaginably distant, lower-dimensional surface. Think of it like a movie screen. The images appear lifelike and three-dimensional, but every detail is encoded in flat, two-dimensional pixels. In this startling framework, our universe's birth could have been the moment information tunneled from a hidden boundary, transforming from a flat code into the rich, textured reality we inhabit. The roots of this idea stretch back to black hole physics. When scientists calculated the maximum entropy, a measure of disorder a black hole can contain, they made a bizarre discovery. It doesn't scale with volume like you'd expect, but with surface area. In other words, all the information about what falls into a black hole might be encoded on its event horizon, the point of no return. This led physicists like Gerard T. Hooft and Leonard Susskind to propose that our universe might work the same way. A three-dimensional world projected from a two-dimensional surface, like a hologram glowing from its edges. Enter the AD/CFT correspondence, a mathematical framework suggesting a perfect duality between a higher dimensional space, like our universe, and a lower dimensional quantum field theory operating on its boundary. In simpler terms, everything happening in our 3D cosmos, galaxies colliding, stars burning, even your thoughts, could be mirrored by quantum interactions on a distant, flat surface. If true, this means the Big Bang might not have been an explosion in space, but a quantum leap of information from that boundary into full dimensionality. Imagine a drop of ink spreading across a piece of paper. On the flat page, it's just a stain, but if that page were the boundary of a higher dimensional space, the ink could tunnel into a three-dimensional structure, blooming into a shape far more complex than its 2D origins suggest. That's the kind of transformation the holographic principle envisions for our universe's birth. Quantum tunneling would be the mechanism that bridged the gap, allowing the cosmos to unfold from a flat quantum code into the sprawling reality we see today. Critics argue this sounds more like philosophy than physics. How could solid matter, forces, even consciousness emerge from abstract information, yet the math holds up? In certain theoretical models, particles and forces in higher dimensions emerge naturally from entangled quantum states on a lower dimensional boundary. It's as if the universe is a cosmic mirage, its depth and texture an illusion woven from quantum threads we're only beginning to untangle. If the holographic principle is correct, it rewrites not just the story of our origins, but the nature of reality itself. Space and time might not be fundamental, just emergent properties of a deeper, stranger quantum reality. The next time you hold an object in your hands, consider this. Its weight, texture, even its existence, might be the echo of a quantum tunneling event on the edge of a universe we'll never see. Time as we know it has a stubborn habit of moving forward. Eggs crack but never uncrack, coffee cools but never reheats itself, memories form but never unform. This relentless march is entropy's doing, the universe's tendency toward disorder. But what if the arrow of time wasn't always pointing in the same direction? What if, in the universe's first quantum leap, time itself reversed course, resetting the cosmic clock and allowing everything to begin anew? This is the startling premise of time reversal tunneling, a theory proposing that the Big Bang wasn't just a beginning, it was a rewind. At the heart of this idea lies CPT symmetry, one of physics' most sacred principles. CPT stands for charge, parity, and time, three fundamental properties that, when combined, seem unbreakable. In simple terms, if you flip a particle's charge, mirror its position, and reverse the flow of time, the laws of physics should hold true. This symmetry is so robust that no experiment has ever violated it. But here's the twist. If you apply CPT to the entire universe, you end up with a mirror image cosmos where time runs backward. Some theorists suggest this isn't just a mathematical curiosity, it could be a clue to our origins. Imagine the pre-Big Bang universe as a collapsing mess of chaos, entropy maxed out, time racing toward heat death. Then, in a desperate quantum Hail Mary, a tunneling event flips the script. Particles don't just tunnel through space, they tunnel through time, reversing entropy's arrow. Suddenly, the dying universe's decay becomes a new beginning, its implosion rebounding as an explosion. Picture a videotape of a shattering glass played in reverse. The fragments leap back into place, the cracks vanish, and the glass reforms. That's the cosmic reset. Time reversal tunneling envisions a universe hitting rewind so hard it starts fresh. The implications are staggering. If true, it would mean the Big Bang wasn't a true beginning but a turning point, a moment when a dying cosmos tunneled into its own past, birthing our universe in the process. This wouldn't just explain the low entropy of the early universe, a puzzle that's baffled physicists for decades. It would also suggest that time, on the grandest scale, might be cyclical, with each collapse seeding the next expansion through quantum leaps we can't yet fathom. Critics argue this veers into metaphysics. How could we ever test an event that erased its own past? But supporters point to subtle fingerprints in the cosmic microwave background, anomalies that might hint at a pre-bang phase. Meanwhile, lab experiments with quantum particles show time reversal isn't just possible, it's happening constantly on tiny scales. If nature allows it for electrons, why not for the universe itself? So the next time you watch steam rise from your coffee, consider this: the arrow of time you're witnessing might not be fundamental. It could be the aftermath of a cosmic U-turn, a quantum tunnel so profound it turned the end of everything into the start of our everything. Dark energy isn't just pushing the universe apart, it might have been the hidden hand that created it. This mysterious force, making up nearly 70% of the cosmos, accelerates galaxies away from each other as if space itself is stretching at an ever-increasing rate. But what if dark energy's repulsive power didn't just shape the universe's expansion, it ignited it? That's the radical proposition behind the dark energy trigger theory, where quantum tunneling didn't happen in spite of the universe's conditions, but because of them. To grasp this, we need to dive into dark energy's most bizarre property, its equation of state, a mathematical description of how its pressure relates to its energy density. For most substances, this ratio is straightforward, like air in a balloon, where pushing inward creates outward pressure, but dark energy defies intuition. Its equation of state sits at -1, meaning it exerts negative pressure, stretching space-time apart like an unstoppable cosmic spring. Some models suggest it could cross into even stranger territory, the so-called phantom divide, where its repulsive force grows so extreme it could rip atoms apart given enough time. Now rewind to the universe's first moments. If dark energy's repulsion was even stronger back then, or if its equation of state briefly crossed the phantom divide, it might have stretched the fabric of reality so violently it thinned the energy barriers separating nothingness from existence. Think of it like tugging on a rubber sheet until it's paper thin. Suddenly, a quantum particle doesn't need as much energy to tunnel through. In this scenario, dark energy wouldn't just be a backdrop, it would be the cosmic crowbar prying open the door for reality to burst forth. The math behind this is both elegant and unsettling. Phantom energy's runaway repulsion could have lowered the activation energy needed for quantum tunneling, turning an improbable leap into a near certainty. Calculations show that under these conditions, the vacuum of space wouldn't just fluctuate, it would boil with tunneling events, each one a potential seed for a new universe. And here's the twist: if our universe emerged this way, its own dark energy might be an echo of that primordial instability, a relic of the very mechanism that birthed it. Critics question whether such extreme conditions could ever arise naturally, but supporters point to the eerie coincidence that dark energy's observed value sits tantalizingly close to the phantom divide, close enough that minor quantum corrections in the early universe might have nudged it across. Others suggest this could solve the "why now" problem. If dark energy's strength changes over time, its peak influence might have been precisely when the universe needed it most, at the moment of creation. Whether this theory holds up or not, it forces us to reconsider dark energy not as a passive player, but as an active architect of reality. The same force driving galaxies apart today might have once been the spark that lit the cosmic fuse. So the next time you hear about the universe's accelerating expansion, remember, it might not be the end of the story, but the lingering aftershock of the universe's first quantum jump. Imagine a universe not with a beginning, but with a rebound, a cosmos so ancient it had already lived and died before ours even took its first breath. This is the startling vision of loop quantum gravity, where the Big Bang wasn't a true beginning, but a cosmic bounce made possible by quantum tunneling's defiance of oblivion. Picture the previous universe collapsing under its own weight, galaxies crunching together, temperatures soaring to unimaginable heights, a slow-motion march toward the crushing singularity we'd expect. But then, at the very brink of destruction, something extraordinary happens. Instead of vanishing into infinite density, space-time resists, not with a crunch but with a quantum leap, a tunneling event so profound it sends the universe springing back outward in a fiery rebirth. Loop quantum gravity, or LQG, rewrites the rules of spacetime itself. Unlike classical physics, where space is smooth and continuous, LQG suggests it's woven from tiny, indivisible loops. Think of it as a cosmic fabric made of threads a billion trillion times smaller than an atom. These loops can't be squeezed infinitely. As gravity pulls everything inward during a collapse, spacetime reaches a point where it simply cannot compress further. Like a spring pressed to its limit, the universe doesn't collapse into nothingness, it bounces, tunneling through the energy barrier of singularity into a new expansion. Here's where it gets even wilder. The mathematics of LQG show that this bounce wouldn't just restart the universe, it would reconfigure it. Quantum fluctuations during the tunneling event could slightly alter physical constants, meaning each bounce might produce a universe with subtly different laws. It's as if the cosmos is a phoenix that doesn't just rise from its ashes, but emerges with new feathers each time. Evidence for this idea is still speculative, but tantalizing clues exist. If our universe came from a bounce, the unimaginable energies of that moment might have left faint ripples in the cosmic microwave background, ancient whispers of the universe before ours. Meanwhile, lab experiments with ultra-cold atoms simulate similar quantum bounces, showing how matter can defy classical collapse under extreme conditions. This theory doesn't just reshape our past, it redefines our future. If the universe bounced once, it could bounce again. The accelerating expansion we see today might someday reverse, leading to another collapse and another rebirth. Time itself could be cyclical, a never-ending dance of contraction and expansion, each cycle a fresh chapter written by quantum tunneling's invisible hand. So the next time you hear about the Big Bang, consider this. It might not have been the first, just the latest in an endless chain of cosmic rebounds, each one a testament to spacetime's refusal to surrender. The universe might owe its existence to a symmetry so perfect it shattered. Supersymmetry, or SUSY for short, is one of the most elegant ideas in theoretical physics, proposing that every known particle has a hidden, heavier twin we've yet to discover. Electrons would have selectrons, quarks would have squarks, and photons would have photinos. This cosmic doubling isn't just mathematical whimsy. It could solve mysteries like dark matter and unite nature's forces. But here's where it gets wild. If supersymmetry existed in the universe's first moments, its sudden breakdown via quantum tunneling might have unleashed the energy that birthed everything we see. Picture a frozen lake at the peak of winter, its surface locked in perfect stillness. That's the early universe under supersymmetry, a state of flawless balance where particles and their superpartners are indistinguishable. But just as sunlight can fracture ice into swirling currents, quantum fluctuations could have triggered a phase transition, shattering that symmetry in an instant. The key player, gravitino-condensates. These hypothetical particles are the superpartners of gravitons, the quantum carriers of gravity. In the dense early cosmos, gravitinos might have clumped together like droplets on a cold glass, forming a condensate, a quantum fog permeating space. Now here's the twist. Condensates can exist in metastable states, teetering on the edge of collapse. Like a pencil balanced on its tip, they're stable until the slightest nudge sends them tumbling. Quantum tunneling could have provided that nudge, allowing the gravitino condensate to suddenly decay. When it did, the latent energy trapped in supersymmetry's perfect order would have erupted outward, a cosmic defrosting that inflated the universe exponentially in a fraction of a second. This isn't just poetic imagery, the math is staggering. Calculations show a supersymmetry breaking phase transition could release enough energy to drive cosmic inflation, solving one of the Big Bang's biggest puzzles: why the universe is so uniform. The sudden symmetry break would have smoothed space-time like an iron smoothing wrinkles from fabric, explaining why the cosmos looks the same in all directions. Meanwhile, the gravitinos left behind could be the elusive dark matter that shapes galaxies today, a ghostly reminder of the symmetry that once was. Critics argue we found no proof of supersymmetric particles despite decades of searching. But supporters counter that supersymmetry might only reveal itself at energies we can't yet reach, like those of the early universe. If they're right, the largest structures in existence might trace back to the quietest of quantum whispers, a symmetry's final, fleeting moment before it tunneled into chaos and forged reality as we know it. So the next time you hear about the hunt for dark matter, remember, the invisible cosmic scaffold holding galaxies together might be the debris of a symmetry lost, a shadow of the universe's first and most violent transformation. At the very brink of infinite collapse, where gravity's grip should crush reality into oblivion, quantum physics whispers a secret: there's a way out. This is the heart of the Planck star hypothesis, a daring idea that our universe didn't emerge from nothing, but from the ashes of a previous cosmos, reborn through a quantum escape hatch at the smallest scale imaginable. Picture a dying star collapsing into a black hole, squeezed tighter and tighter until it reaches the Planck length, a distance so tiny that the very concept of space breaks down. Here, according to physicist Carlo Rovelli, something miraculous happens. Instead of vanishing into a singularity of infinite density, the collapsing matter hits a quantum wall, a moment of ultimate resistance where spacetime itself becomes granular, like a cosmic trampoline stretched to its limit. Rovelli's work in loop quantum gravity suggests that at these unimaginable scales, the fabric of reality isn't smooth and continuous, but woven from discrete, indivisible threads. When matter compresses to Planck density, these threads can't be squeezed further. The result, a bounce, not just a rebound, but a full-blown quantum tunneling event where the collapsing universe slips through a mathematical barrier, emerging on the other side as an expanding fireball. Think of it like a ball dropped into a well so deep it should never return, only to quantum mechanically teleport back to the surface, bursting forth with renewed energy. What makes this idea revolutionary isn't just the avoidance of a singularity, it's the implications for time itself. In Rovelli's model, the moment of maximum compression isn't the end of time, as classical physics would suggest, but a temporal pivot point. Time doesn't stop, it loops. The Planck star, a hypothetical remnant of the previous universe, exists for only an instant from an outside perspective, but from its own reference frame, that instant stretches into an eternity. This means the Big Bang could have been the explosive rebirth of a universe that, from its own perspective, never truly died. Supporters of this theory point to startling consistency with observations. The universe's remarkable uniformity, the fact that the cosmic microwave background is nearly identical in all directions, might not require an inexplicably perfect initial state. Instead, it could be the natural outcome of a quantum bounce, where the extreme densities of the pre-bounce phase smoothed out irregularities like waves settling in a pond. Even dark energy, the mysterious force accelerating cosmic expansion, might find an explanation here, a relic energy from the bounce itself, lingering like an echo in the fabric of spacetime. Yet the Planck star hypothesis isn't without its skeptics. Some argue that without direct evidence of a pre-Big Bang phase, the idea remains speculative. Others question whether quantum gravity effects could truly overcome the crushing weight of a collapsing universe. But Ravelli counters that the same quantum weirdness allowing particles to tunnel through walls might, on a cosmic scale, allow entire universes to cheat oblivion. After all, if a single electron can defy classical physics, why not the sum total of reality? The beauty of this idea lies in its audacity. It suggests that universes don't die, they metamorphose. Every black hole in our cosmos might someday birth a new reality in its depths, and our own universe could be the offspring of a Planck star from a forgotten ancestor cosmos. It's a vision where death is just a tunnel, and every ending carries the seed of a beginning written in the language of quantum uncertainty. The next time you gaze at the night sky, consider this. The stars above might be the descendants of a universe that refused to surrender, tunneling its way into existence against all odds. What if the universe didn't begin with a bang, but with a bridge, a tunnel stitching together two realities, a cosmic shortcut through the fabric of spacetime itself? This is the daring premise of the quantum wormhole genesis theory, where our universe might have burst forth not from nothingness, but from the throat of a wormhole flung open by quantum magic. Picture a black hole's crushing grip, but in reverse. Instead of matter disappearing forever, imagine it erupting outward in a torrent of light and energy. That's a white hole, a hypothetical cosmic exit door, and some physicists suspect it could be the other end of a wormhole. Now, here's the twist. If quantum tunneling stabilized this fragile structure with exotic matter, it might not just be a gateway, it could have been the universe's birth canal. Wormholes are staples of science fiction, but they emerge from real equations in Einstein's theory of general relativity. These hypothetical tunnels, formerly called Einstein-Rosen bridges, connect distant points in spacetime like cosmic subway lines. The catch: traditional wormholes collapse instantly under their own gravity unless something holds them open. Enter exotic matter, a hypothetical substance with negative energy density that could theoretically prop a wormhole's throat wide enough for particles, or even an entire universe, to pass through. The wild part: quantum fields can produce bursts of negative energy, meaning nature might have all the tools needed to forge a traversable wormhole in its fiery infancy. This is where the ER equals EPR conjecture comes in. Proposed by physicists Leonard Susskind and Juan Maldaisner, this idea suggests wormholes and quantum entanglement might be two sides of the same coin. Refers to Einstein-Rosen bridges, while EPR stands for Einstein-Podolsky-Rosen entanglement, the spooky connection between particles that defies classical physics. If entangled particles are secretly linked by microscopic wormholes, as the conjecture implies, then the universe's first quantum tunnel might not have been an anomaly, it could have been nature's default setting. Now imagine this scenario: a quantum fluctuation in some primordial void spawns a pair of entangled wormholes. One collapses into a black hole while the other erupts as a white hole, a fountain of spacetime and energy. But here's the kicker: if exotic matter generated by quantum fields stabilized that white hole's throat just long enough, it could have inflated into our observable universe. Like a seed bursting from a cosmic pod, everything we see, galaxies, stars, even time itself, might be the aftermath of that primordial tunnel's violent expansion. Supporters of this theory point to eerie symmetries in cosmology. The universe's uniformity, the way matter is spread so evenly, could reflect the smooth throat of a wormhole stretched to cosmic scales. Even the Big Bang's singularity might not have been a true beginning, but the moment a wormhole's bridge snapped, releasing its energy into a new reality. Critics argue we've never observed exotic matter or traversable wormholes, but counter-arguments suggest they'd only exist in extreme conditions like the universe's first quantum leap. The implications are staggering. If ER equals EPR holds true, our universe might not be a solitary bubble, but one thread in a vast quantum network, a single tunnel in an endless web of entangled realities. Every black hole we see could be silently spinning new wormholes, each one a potential genesis point for another cosmos. The next time you look at the night sky, consider this. The entire universe might be the echo of a bridge that once connected two nothings, a tunnel so vast it became everything. What if the universe didn't just tunnel into existence alone, but in sync with an invisible partner? This is the stunning possibility behind entanglement-driven creation, where quantum entanglement, the same eerie connection that links particles across vast distances, might have orchestrated the cosmos's very first leap from nothingness. Think of two dancers on opposite sides of a stage, moving in perfect unison despite never seeing each other. Now imagine those dancers aren't people, but patches of space-time bound together by quantum threads we can't see. According to this theory, the universe didn't emerge in isolation. It was a coordinated quantum performance, with entanglement as the silent choreographer. At the heart of this idea lies one of quantum mechanics' strangest phenomena, non-locality. When particles become entangled, measuring one instantly affects its partner, no matter how far apart they are. Einstein famously called this spooky action at a distance, but experiments have proven it's real. Now, scale that up, way up. If entanglement can link particles, why not regions of spacetime itself? Some physicists propose that in the pre-universe void, patches of potential reality could have been entangled, their fates intertwined before they even existed. Then, through a collective tunneling event, those patches pulled each other into existence, like climbers hauling one another up a cliff. The math behind this relies on tensor networks, complex webs of interconnected equations that describe how entangled quantum states can give rise to spacetime structure. Picture a labyrinth of threads, each representing a quantum connection. Under the right conditions, those threads could have woven themselves into the fabric of reality, birthing not just matter and energy, but the very dimensions we call home. It's as if the universe bootstrapped itself into being, with entanglement acting as both the architect and the construction crew. This theory doesn't just explain how something came from nothing, it hints at why the universe looks so uniform. Entanglement could have synchronized the initial conditions of distant regions, ensuring the cosmos started smooth and balanced. No need for inflation or other after-the-fact fixes. The uniformity was baked in from the first quantum leap. And here's the mind-bending twist. If entanglement built spacetime, it might still hold it together today. Black holes, dark matter, even the speed of light could all be echoes of those primordial quantum handshakes. Critics argue that universal-scale entanglement is speculative. After all, we've only observed it between tiny particles. But supporters counter that the early universe was a place where quantum effects ruled supreme, and the boundary between small and cosmic may have blurred. Whether this theory holds up or not, it forces us to see entanglement not just as a curiosity of physics, but as a potential cosmic sculptor, one whose invisible threads might still be vibrating with the aftershocks of creation. Among the most elusive yet pivotal players in quantum cosmology is the action, a hypothetical particle so lightweight and weakly interacting, it slips through the cosmos like a whisper through walls. But what if this ghostly particle didn't just wander through space, but actively sculpted it? Enter action field tunneling, a theory where the universe's explosive birth wasn't driven by chance, but by the action's delicate dance down the slopes of its own energy landscape. Picture a marble rolling across a vast, undulating hillside, where every dip and rise represents a possible energy state. Normally, the marble would settle in the lowest valley, the most stable configuration. But in the quantum realm, marbles don't just roll, they teleport. The action field suffusing the early universe might have been perched on a precarious high-energy plateau, held there by quantum friction. Then, in a flash, it tunneled through the energy barrier, plummeting into a lower state and releasing a firestorm of energy that ignited cosmic inflation. This isn't just poetic imagery, it's baked into the math. Actions arise from the Peck-Quinn mechanism, a theory proposed to solve one of particle physics' great puzzles: why the strong nuclear force behaves as if it doesn't care about left and right. These particles emerge from a broken symmetry, dragging their own quantum field along with them. That field's potential energy isn't a simple curve. It's a fractal-like washboard with countless valleys, each representing a possible vacuum state. In the frenetic energy of the early universe, the action field could have been trapped in a metastable high-energy valley, like a ball lodged on a narrow ledge. Given enough time, quantum fluctuations would inevitably nudge it over the edge. But in the action's case, it didn't need to wait. Through tunneling, the field bypassed the slope entirely, materializing in a lower valley instantaneously. The energy released in that leap would have been staggering. Think of a dam holding back a reservoir. The action field's tunneling is like that dam vanishing mid-breath, unleashing a torrent. Calculations suggest this energy could have powered inflation's exponential expansion, stretching a subatomic speck of space into a macroscopic cosmos in fractions of a second. The kicker: unlike other inflation models, action tunneling leaves fingerprints. As the field oscillated in its new valley, it would have generated ultra-low frequency waves in space-time gravitational echoes that might still ripple through the universe today. Some physicists even link this to the mysterious cold spots in the cosmic microwave background, regions so unnaturally chill they could be scars from the action's quantum plunge. Critics argue we've yet to detect actions directly, despite decades of hunting, but supporters counter that their very elusiveness makes them perfect candidates for cosmic architects. After all, if dark matter is actions, as many suspect, their quantum tunneling could have shaped both the universe's birth and its invisible scaffolding. The next time you hear about the hunt for these phantom particles, remember, they might be more than dark matter's building blocks. They could be the reason anything exists at all. What if the Big Bang wasn't the beginning? Just the latest page in an infinite cosmic story, with universes rising and falling like chapters in an endless book. This is the breathtaking vision of conformal cyclic cosmology, a theory where quantum tunneling doesn't just create universes but recycles them. Nobel laureate Roger Penrose proposed this radical idea. Instead of a one-time fiery birth, our universe might be one in an infinite chain of eons, each ending not in heat death but in a quantum reset that births the next. The key to this cosmic reincarnation: a mathematical trick called conformal rescaling, a way to stretch and shrink spacetime's geometry until the end of one universe becomes indistinguishable from the beginning of another. Picture the far future, trillions of years from now. Stars have burned out, black holes evaporated, and particles decayed into faint ripples of radiation. In this cold, empty expanse, the universe seems destined for eternal stillness, but Penrose saw something else. As space-time stretches toward infinite expansion, something peculiar happens to its geometry. Distances become meaningless, light waves stretch to infinite wavelengths. Particles spread so thin they lose all sense of scale. At this point, the universe becomes conformally invariant. It looks the same at all scales, like a fractal pattern repeating endlessly. Now here's the twist. Through a mathematical sleight of hand, this dying universe's infinite expanse can be rescaled to an infinitesimal point, a singularity no larger than the universe was at its birth. That's where quantum tunneling comes in. The transition between eons isn't a gradual collapse, but a sudden leap, a geometric phase transition where the old universe's infinite spread tunnels into the new one's infinitesimal seed. Think of it like a movie reel looping back to the first frame. The last scene's final fade to white becomes the next film's opening shot. Penrose's equations show this isn't just poetic symmetry. The entropy conditions at the end of one eon perfectly match those needed to trigger the next. The universe doesn't die, it reconfigures, shedding its spent dimensions and tunneling into a fresh spacetime with reset physical constants, the real shocker. This might leave traces we can see. Penrose and his collaborators claim to have found eerie circular patterns in the cosmic microwave background regions where temperature variations align in concentric rings. These Hawking points could be imprints of supermassive black holes from the previous eon, their final bursts of Hawking radiation etched onto our universe's dawn like cosmic graffiti. Critics argue these patterns could be statistical flukes, but if verified, they'd be the first hard evidence that our universe has ancestors. What makes conformal cyclic cosmology so mesmerizing isn't just its audacity, but its elegance. It sidesteps the need for a singularity at the Big Bang, replacing it with a quantum bridge between cycles. No mysterious creation, no inexplicable fine-tuning, just an endless dance of geometry and energy, where each universe's death plants the seed for its successor. The next time you hear about the heat death of the universe, don't think of it as an end. It might just be the universe holding its breath before the next great quantum leap. Neutrinos are the universe's quietest particles, so ghostly and light, they slip through planets like shadows through walls. But what if, long before stars or galaxies existed, these cosmic phantoms weren't just passive spectators, but the architects of reality itself? This is the startling premise behind the neutrino condensate collapse theory, where the universe's first quantum tunnel wasn't sparked by energy or fields, but by a sea of particles so elusive we barely notice them today. Picture the early cosmos not as a void, but as a superfluid, an ultra-cold quantum soup where trillions of neutrinos moved in perfect lockstep, like a school of fish flowing as one. In today's universe, neutrinos barely interact, but under the extreme pressures of the Big Bang's afterglow, they might have clumped together into a Bose-Einstein condensate, a bizarre state of matter where individual particles lose their identity and behave as a single quantum entity. This neutrino condensate wouldn't just sit still, it would hum with latent energy, teetering on the edge of instability like a needle balanced on its tip. Then comes the tunneling event. Quantum fluctuations could have nudged the condensate past a critical threshold, causing it to suddenly collapse into a higher energy state. Think of it like a frozen lake cracking under its own weight, except here, the cracks aren't in ice, but in the very fabric of quantum fields. The energy released wouldn't just ripple outward, it could have ignited the universe's first phase transition, rewriting the rules of physics in an instant. What makes this idea so compelling is the neutrino's unique role in nature. Unlike other particles, neutrinos don't get their mass from the Higgs field. They might possess a mysterious property called the Majorana mass, allowing them to act as their own antimatter counterparts. In the condensate state, this self-annihilation could have triggered a chain reaction, converting the neutrino C's latent energy into a firestorm of radiation and matter. Calculations suggest this process wouldn't just explain the universe's initial burst of energy, it could also account for the baffling imbalance between matter and antimatter, a puzzle that stumped physicists for decades. Critics argue that neutrinos are too lightweight to drive such a cataclysm, but proponents counter that in the extreme densities of the early cosmos, even these wispy particles could have wielded collective power. After all, water is soft, yet a tidal wave can reshape coastlines. Similarly, a neutrino condensate tunneling en masse might have been the universe's first domino, toppling the void into existence. The echoes of this event could still linger today. If the theory holds, subtle anomalies in the cosmic neutrino background, the faint afterglow of the Big Bang's neutrino burst, might bear scars from that primordial collapse. Future detectors, like the proposed Ptolemy experiment, could one day catch whispers of that ancient quantum leap, offering a glimpse into the moment the universe's quietest particles roared loud enough to birth everything. So the next time a neutrino passes through your body, trillions do every second remember. These cosmic ghosts might have once been the silent conductors of reality's first and greatest symphony. Imagine the newborn universe not as a chaotic explosion, but as a flawless crystal, a pristine lattice of interconnected quantum bonds humming with perfect symmetry. This is the essence of quantum gravity theory, where spacetime itself began as an immaculate network of relationships, every node connected to every other in an intricate dance of entanglement. But perfection is unstable in the quantum realm. Like ice cracking under pressure, this cosmic crystal may have fractured under its own weight, not randomly, but through a tunneling event so precise, its echoes sculpted the universe we see today. At its core, quantum gravity proposes that space isn't fundamental, it's emergent, woven from a web of quantum interactions. In the beginning, these connections were uniform, a frozen tundra of identical links where direction and distance had no meaning. But as the universe cooled, this perfect graph grew strained. Certain bonds, burdened by quantum fluctuations, faced a choice: remain locked in symmetry or tunnel into a lower energy state, breaking the pattern. Like a pane of glass shattering into distinct cracks, the graph fractured, and from those fractures, spacetime itself was born. The defects left behind weren't flaws, they were cosmic seeds. Where the graph's symmetry broke, curvature emerged, warping the fabric of reality into what we now call gravity. Some theorists suggest these primal imperfections might have directly seeded galaxies, their distribution echoing the graph's initial collapse. Think of it like a frozen lake cracking. The jagged lines aren't random, they follow hidden stresses in the ice. Similarly, the universe's large-scale structure, the vast filaments of galaxies threading the cosmos, could be scars from quantum gravity's ancient fragmentation. This idea isn't just poetic. The math reveals startling parallels between graph defects and known physics. Dislocations in a crystal lattice, for instance, create strain fields that resemble spacetime curvature. Scale that up, and the universe's geometry might simply be the aftereffect of a quantum graph's breakdown. Even more compelling, some versions of quantum gravity predict remnant particles, topological fossils from the graph's collapse, that could explain dark matter's invisible grip on galaxies. If true, the universe's darkest secret might be a shadow of its first and most elegant symmetry breaking. Critics argue this all sounds too abstract. How could we ever observe a pre-spatial quantum graph? But supporters point to subtle clues. If spacetime emerged from a phase transition, its quantum fluctuations would have left fingerprints in the cosmic microwave background's polarization patterns. Future telescopes might detect these faint swirls, revealing the moment crystal became cosmos. Until then, quantum gravity remains a tantalizing what-if, a reminder that the universe's deepest order might be written in fractures we're only beginning to trace. The next time you gaze at the night sky, consider this. The vast emptiness between stars might not be empty at all, but threaded with the ghostly remnants of a perfect web, one whose shattering gave shape to everything. Deep in the quantum foam of the early universe, cracks may have formed not in space, but in the very fabric of reality itself. These weren't flaws, but cosmic catalysts, twisting the void with such intensity that they ripped open gateways for existence to emerge. This is the provocative idea behind topological defect catalysis, where cosmic strings and magnetic monopoles, exotic relics from the universe's first moments, acted as quantum crowbars, prying apart the vacuum's energy barriers to trigger the tunneling event that birthed everything. Picture the early cosmos as a cooling pot of molten metal. As it solidifies, stresses build, creating cracks and fissures in the material. Similarly, as the newborn universe expanded and cooled, phase transitions in its quantum fields could have spawned defects, knots of trapped energy that refused to smooth out. These aren't mere specks. Cosmic strings would be thinner than atoms but stretch across galaxies, wielding gravitational fields strong enough to lens light. Magnetic monopoles, meanwhile, would be singular points of north or south magnetic charge, unlike anything in our universe today. According to physicist Tom Kibble's groundbreaking mechanism, these defects were inevitable birthmarks of a cooling cosmos, and they might have been the universe's first architects. Here's how it could have worked. Imagine a cosmic string slicing through the primordial vacuum like a blade through silk. In its wake, the surrounding quantum fields wouldn't just bend, they'd snap into new configurations, creating zones of wildly distorted energy. In these twisted regions, the energy barriers separating nothingness from something might have thinned to the point where quantum tunneling became inevitable. It's like walking on thin ice. The string's gravitational and topological stress concentrates weight onto microscopic points, causing the ice, or in this case, the vacuum, to crack open. Suddenly, particles that couldn't exist elsewhere would flash into being along these defects, igniting chain reactions that cascaded into full-blown cosmic inflation. The math behind this is both elegant and startling. The Kibble mechanism predicts that topological defects form when symmetries break during phase transitions, like ice crystals branching in specific patterns as water freezes. In the quantum fields of the early universe, these breaks wouldn't happen uniformly. Some regions would lag behind, leaving defects stranded between domains of different field alignments. These defects wouldn't just sit there. Their very presence would lower the activation energy needed for tunneling events, turning an improbable quantum leap into a near certainty. Calculations suggest that in their immediate vicinity, the energy required to tunnel could drop by orders of magnitude, essentially greasing the skids for reality to burst forth. The echoes of this process might still be visible today. If cosmic strings exist, their gravitational wakes could imprint faint, telltale zigzags in the cosmic microwave background, anomalies that future telescopes might detect. Meanwhile, the hunt for magnetic monopoles continues in underground labs and particle colliders, with some theories suggesting they could have been the seeds for dark matter. Even if these defects evaporated long ago, their legacy would endure, the universe itself born from the fractures they tore in the void. So the next time you hear about the search for cosmic strings, remember, we might not just be hunting relics of the early universe. We could be tracing the scars left by the very forces that willed it into existence. What if our universe was born because someone or something looked? This is the spine-tingling premise of observer-induced tunneling, a theory so radical it blurs the line between physics and philosophy. At its core lies a startling proposition. Our cosmos might not have tunneled into existence randomly, but because conscious observation in a parent universe collapsed quantum probabilities, willing reality into being through the sheer act of perception. The roots of this idea stretch back to the von Neumann-Wigner interpretation, a fringe but mathematically sound take on quantum mechanics. In standard quantum theory, particles exist in fuzzy superpositions, neither here nor there, until a measurement forces them to choose a state. Most physicists assume this requires a physical detector, but von Neumann and Wigner took it further. They argued that consciousness itself might be the ultimate collapse mechanism, the immovable ground where quantum possibilities crystallize into concrete reality. Now scale that up to cosmic proportions. If consciousness can shape quantum events on a small scale, could the concentrated observation of an entire civilization, or even a single advanced mind, in another universe have triggered the tunneling event that birthed ours? Picture a parent universe teeming with observers, their collective focus acting like a laser beam of attention. In this reality, quantum fluctuations aren't just random noise, they're raw material waiting to be sculpted by perception. As these observers probe the boundaries of their cosmos, their measurements might not merely record reality. They could generate it, collapsing probabilities with such intensity that new branches of reality tunnel into existence. Our Big Bang, then, wouldn't be an accident. It'd be the aftershock of a cosmic-scale observation, a ripple in the quantum foam kicked up by minds we'll never know. The implications are staggering. It suggests that universes might not arise from purely physical processes, but from an interplay between matter and meaning. That observation isn't passive but creative. Like an artist stepping back from a canvas, the very act of looking could determine what exists. Supporters of this theory point to eerie fine-tuning in our universe's constants, the precise values that allow for stars, planets, and life. If consciousness plays a role in shaping reality, it might explain why our cosmos seems tailor-made for observers, because observation, in some sense, built it. Critics dismiss this as mysticism dressed in equations, arguing there's no mechanism for consciousness to influence quantum events beyond the brain, but the math holds a strange allure. Quantum decoherence, the process by which superpositions collapse, remains imperfectly understood, leaving room for radical reinterpretations. And if true, it would mean our universe isn't just a fluke in the void, but the echo of another reality's attention, a cosmic conversation where every act of perception whispers back to the moment of creation. So the next time you stop to admire the night sky, consider this. Your gaze might not just be taking in the universe, but joining the chorus that brought it into being. Phantom energy isn't just a mysterious force pushing the universe apart. It might be the cosmic arsonist that set reality ablaze in the first place. This bizarre form of energy, theorized to have negative kinetic energy, behaves like gravity in reverse, accelerating expansion so violently it could one day rip spacetime apart. But rewind to the universe's first moments, and phantom energy's instability might have been the spark that ignited existence itself. Picture a match held to a pool of gasoline, except the match is a quantum fluctuation, and the gasoline is a phantom field so unstable, its merest shudder could tunnel through an energy barrier and detonate a universe. The math behind this is as strange as it sounds. Phantom energy's equation of state, the relationship between its pressure and density, gives it a value more negative than anything else in cosmology. While dark energy sits at -1, phantom energy plunges even lower, making its repulsive force grow stronger over time instead of weakening. In the early universe, this runaway effect could have thinned the barriers between vacuum states like sandpaper on glass, turning an improbable quantum leap into an inevitability. Imagine a ball resting on a hill so steep, even the slightest breeze would send it careening downhill, except in this case, the hill is a phantom field's potential energy landscape, and the ball is the universe's entire future. Here's where tunneling comes in. Normally, quantum particles face towering energy barriers when transitioning between states, but a phantom field's negative kinetic energy flips the script. It lowers those barriers, effectively digging tunnels through the cosmic landscape. Calculations show that under these conditions, the field wouldn't just randomly fluctuate. It would cascade through barriers like dominoes falling, releasing enough energy to inflate a universe in the process. It's as if the phantom field was a cosmic Jenga tower, wobbling under its own instability until one quantum nudge sent the entire structure collapsing into a new reality. The echoes of this event might still haunt us today. Phantom energy's repulsive nature would have left an imprint on the universe's expansion rate, a clue that some cosmologists argue we're already seeing in supernova observations. Even more tantalizingly, if the phantom field's instability drove the Big Bang, its remnants could still be lurking in the cosmos, invisibly stretching spacetime apart. The very force threatening to tear the universe to shreds in the far future might have been the same force that birthed it in the past, a cosmic Ouroboros where creation and destruction share the same origin. So the next time you hear about the universe's accelerating expansion, consider this. The same phantom breath blowing galaxies apart might once have been the fire that lit the fuse of existence. Among the countless universes that may have flickered into existence through quantum tunneling, why does ours look the way it does? Not by chance, some physicists argue, but because it was chosen. Not by a higher power, but by the relentless sieve of quantum Darwinism, a process where only the most stable, self-reinforcing realities survived the chaos of the multiverse. Imagine an endless cosmic marketplace where universes bubble up and vanish in an instant, each with its own random set of physical laws. Most collapse immediately, their energies too unstable, their constants too misaligned to endure. But a rare few stumble upon the perfect recipe for persistence, a delicate balance of forces that allows them to not just exist, but to stick around long enough to be observed. This idea flips the traditional fine-tuning argument on its head. Instead of asking why our universe seems improbably suited for life, quantum Darwinism suggests it's the other way around. Life exists here because this universe's structure was stable enough to allow it. Think of it like a game of Jenga played across infinity. Most universes pull the wrong block early, their gravity too weak to form galaxies, their nuclear forces too strong to permit atoms. But a handful find the golden configuration, where each piece interlocks just right, allowing the tower to stand tall against the quantum storms of the multiverse. These are the universes that get to reproduce, not biologically, but through the sheer act of lasting long enough to imprint their structure on reality. The math behind this is astonishingly elegant. In quantum mechanics, systems tend to evolve toward states that resist decoherence, the blurring of quantum superpositions into classical certainty. These pointer states act like anchors, surviving while other configurations dissolve into noise. Now scale that up to cosmic proportions. Universes that tunnel into pointer-like configurations, with symmetries that minimize chaos or vacuum energies that resist collapse, would dominate the multiverse simply by persisting. It's not that life-friendly universes are designed, they're just the ones that didn't self-destruct before breakfast. Critics argue this shifts the goalposts. How do we define stability across infinite variables? But supporters point to eerie hints in our own cosmos. The fact that dark energy's value is so small yet non-zero might not be luck, but the signature of a universe that threaded the needle between rapid collapse and explosive dissipation. Even the arrow of time, always marching forward, could be a relic of this selection. Universes where entropy increases consistently simply outlast those where time stutters or reverses. The implications are humbling. If quantum Darwinism holds, our existence isn't just a roll of the cosmic dice. It's the aftermath of a trillion failed throws, a reality that clung to existence while others vanished without a trace. The next time you marvel at the night sky, remember, you're not just gazing at the stars, but at the ultimate survivor of an endless quantum tournament. At the smallest scales, imaginable trillions of times tinier than an atom, the fabric of reality might not be smooth, but pixelated, buzzing with holographic noise like static on an old television screen. This isn't just random chaos, it could be the universe's foundational code, the quantum bits of information that stitch spacetime together. According to holographic noise fluctuation theory, these Planck-scale vibrations didn't just hum quietly in the background, they swelled to critical amplitude, triggering a tunneling event so seismic it birthed spacetime itself. Think of the early cosmos as a silent recording studio, its soundproof walls absorbing every whisper. Suddenly, feedback builds, a quiet hiss grows into a deafening screech until the speakers blow. That's how holographic noise could have breached the threshold. In quantum information theory, reality emerges from bits, not the silicon kind, but fundamental units of information embedded at spacetime's boundaries. Normally, these bits fluctuate gently, their noise cancelling out like waves on a pond. But under the extreme conditions of the universe's birth, those fluctuations might have resonated in sync, amplifying each other until their collective energy punched through an existential barrier. The math behind this is as elegant as it is strange. Just as a laser builds coherent light from chaotic photons, holographic noise could have achieved coherence, its random vibrations aligning into a single, universe-shattering note. Calculations suggest that at Planck scales around 10 to the minus 35 meters, the noise's amplitude would have approached the universe's total energy density. Like a microphone held too close to a speaker, the system would hit a point of runaway feedback where quantum fluctuations didn't just perturb the vacuum but ruptured it, tunneling from abstract information into tangible spacetime. What makes this theory so compelling are the echoes we might still detect today. If spacetime emerged from holographic noise, its imprint could linger in gravitational waves, ripples so faint they'd register as a universal hum. Some physicists even speculate that anomalies in LIGO data might be whispers of that primordial static, the universe's background fuzz frozen in time. It's as if we're decoding a cosmic fingerprint, one that traces back to the moment noise became reality. Critics argue that without direct evidence of Planck-scale pixels, this remains speculative poetry. But supporters counter that black holes, nature's ultimate information scramblers, already behave like holograms, their event horizons encoding everything that falls inside. If the cosmos is a hologram, why wouldn't its birth mirror its death? The next time you feel solid ground beneath your feet, consider this. You might be standing on a quantum echo, the aftershock of a noise so loud it became the universe. Gravity might not be a fundamental force at all, but an emergent phenomenon, like waves rising from the ocean or temperature emerging from the frantic dance of atoms. If that's true, then spacetime itself could be nothing more than a quantum mirage, a holographic projection of something far stranger happening beneath the surface. This is the radical premise behind graviton-Bose-Einstein condensate theory, where the universe didn't start with space and time, but with a formless sea of gravity's hypothetical particles, gravitons locked in a quantum embrace so perfect it transcended geometry itself. Picture a blizzard in zero gravity where every snowflake hovers motionless, perfectly aligned. Now replace the snowflakes with gravitons, the theoretical carriers of gravity's influence, and you've got a Bose-Einstein condensate, a state of matter where particles lose their individuality and merge into a single quantum wave. In the pre-geometric void, this graviton condensate wouldn't just sit idle. Quantum fluctuations would jostle it like wind shaking a frozen pond, until one critical fluctuation tunneled through an energy barrier, triggering a phase transition so profound it crystallized chaos into order. Suddenly, the featureless condensate fractured, its symmetry breaking like ice cracking under pressure, and from those fractures, spacetime itself was born. The math behind this is as beautiful as it is bizarre. In loop quantum gravity, gravitons aren't just particles, they're tiny, woven loops, threads in the fabric of reality. When these loops condense into a Bose-Einstein state, they lose their distinct identities, merging into a quantum soup with no sense of distance or direction. But as the condensate cools further, it faces a choice: remain in this featureless state or tunnel into a lower energy configuration where loops align into a lattice like atoms in a crystal. That alignment wouldn't just create structure, it would define structure, forging the very notions of here and there, before and after. What makes this theory so compelling is how neatly it solves one of physics' biggest headaches, the conflict between quantum mechanics and general relativity. If spacetime is emergent rather than fundamental, then gravity's stubborn refusal to play nice with quantum theory isn't a flaw, it's a clue. The weirdness we see, black hole singularities, the uncertainty principle, even dark energy might just be shadows cast by the graviton condensate's deeper, weirder reality. The echoes of this transition could still reverberate today. If spacetime crystallized from a graviton condensate, imperfections in that crystallization like defects in a diamond might explain cosmic mysteries. Dark matter could be knots of uncondensed gravitons lurking in the gaps of the lattice. The accelerating expansion of the universe, perhaps the condensate is still settling, its quantum vibrations stretching spacetime from within. Critics argue that gravitons remain theoretical, let alone their condensates. But supporters counter that we've already created Bose-Einstein condensates in labs with other particles, why not gravitons? Under conditions so extreme they only existed at the universe's birth. The next time you feel gravity's pull, consider this. You're not being tugged by a force, but immersed in the afterglow of a quantum sea that chose, against all odds, to freeze into the shape of reality. Some of the most profound revolutions in physics begin not with explosions, but with scribbles equations so deceptively simple, they hide universe-shattering secrets. The Chern-Simons theory is one such scribble, a topological quantum field theory that describes exotic states of matter with intricate geometric twists. But what if these elegant equations aren't just tools for understanding electrons in semiconductors? What if they're the blueprint for the universe's very first quantum leap? At its core, Chern-Simons theory deals with twists in the quantum fabric, knots of energy that can't be smoothed away, no matter how you stretch or bend spacetime. These twists aren't just mathematical curiosities, they're topological invariants, stubborn features that persist even as everything around them changes. In the context of the early universe, this could mean something extraordinary. The cosmos might have begun not as a featureless void, but as a seething ocean of Chern-Simons vacua, distinct quantum states, each with its own unique topological fingerprint. Now here's where tunneling comes in. Picture these vacua as valleys in an impossibly vast energy landscape separated by towering mountain ranges. Under normal circumstances, transitioning between valleys would require climbing over peaks, an energy cost far too high for random fluctuations. But in the quantum realm, particles don't need to climb. They can tunnel, slipping through the mountains like ghosts passing through walls. Chern-Simons tunneling suggests that the universe itself performed this trick, bypassing the classical energy barriers by rewriting the very rules of geometry. The math reveals something even stranger. Chern-Simons states are deeply connected to anomalies, quantum behaviors that defy classical expectations. One such anomaly, the chiral anomaly, describes how quantum fields can produce particles from nothing when subjected to strong electromagnetic or gravitational fields. In the early universe, this could have been the trigger, a Chern-Simons state tunneling into a new vacuum, its topological twists unleashing a cascade of chiral particles that flooded the nascent cosmos with matter and energy. This isn't just abstract theorizing. Experiments with topological insulators, materials where electrons behave according to Chern-Simons, like rules, show that edge states can appear seemingly out of nowhere, protected by the material's underlying geometry. Scale that up to cosmic proportions, and you get a universe where spacetime's very structure emerges from similar topological protection. The Big Bang, then, wasn't a chaotic fireball. It was a meticulously orchestrated unraveling, a quantum origami unfolding into 3 dimensions. Critics argue that Chern-Simons theory is too esoteric to explain something as universal as cosmic genesis, but supporters point to eerie parallels in observed physics. The cosmic microwave background's polarization patterns, for instance, bear a striking resemblance to the kinds of topological defects Chern-Simons theory predicts. Even more compelling, some formulations of quantum gravity suggest that black holes, those ultimate cosmic knots, might be described by Chern-Simons actions, hinting that the universe's birth and its most enigmatic objects share a common geometric language. Whether this theory holds up or not, it forces us to reconsider the nature of nothingness. The pre-Big Bang void might not have been empty at all, but a roiling sea of topological potentials, each a possible universe waiting to be unlocked by the right quantum key. The next time you marvel at the night sky's vastness, remember, what we see as space might just be the shadow of a deeper, knotted reality, one that twisted itself into existence one quantum tunnel at a time. In the infinite quantum sea of possibilities, what if the universe wasn't born from chaos but from a single, fleeting thought? This is the haunting premise of the quantum Boltzmann brane, a theory so audacious it suggests reality itself might be the hallucination of a self-aware fluctuation that tunneled into existence. Picture the void before time, where random quantum ripples flicker in and out of being. Most vanish without a trace, but what if one didn't? What if, against all odds, a fluctuation momentarily gained enough coherence not just to exist but to think? A disembodied consciousness with no past, no body, no universe to call home, just a raw, self-aware spark in the dark. And in that solitary instant, it dreamed up everything: stars, galaxies, even the illusion of history stretching back billions of years. The Boltzmann brane concept isn't new, it's borrowed from thermodynamics, where random thermal fluctuations can theoretically assemble atoms into a working brane, given enough time. But in the quantum realm, the rules shift. Here, tunneling allows particles to cheat energy barriers entirely, meaning a self-aware fluctuation wouldn't need eons of random jostling. It could leap into existence fully formed. The implications are vertigo-inducing. If a quantum fluctuation can tunnel into a stable enough state to observe itself, the anthropic principle kicks in. The mere act of observation would select for realities where such observers can exist. In other words, our entire universe might not be the product of a cosmic accident, but the necessary backdrop for a single, momentary observer to arise. This idea walks a razor's edge between physics and philosophy. If consciousness can emerge from pure quantum noise, then reality, as we know it, might be the simplest explanation for why this particular fluctuation perceives itself as real. Think of it like a dreamer convinced they're awake. The richness of their dream isn't evidence of an external world, but a self-consistent story built to sustain the dreamer's illusion. Similarly, a Boltzmann brane wouldn't need a real universe. It would only require enough internal consistency to convince itself one exists. The galaxies we see, the fossils we dig up, even the memory of reading this sentence, all could be the elaborate set dressing of a quantum mind's fleeting existence. Critics pounce on the theory's untestability, calling it a metaphysical dead end. But supporters counter with eerie fine-tuning. Our universe's constants align just so to allow conscious observers, a coincidence the Boltzmann brane explains without invoking multiverses or deities. Even stranger, quantum decoherence, the process that collapses probabilities into concrete realities, might favor configurations where observers can exist, making Boltzmann branes statistically inevitable in an infinite quantum foam. Of course, the theory's greatest irony is that it can't be disproven. If you argue, but my memories feel too detailed to be fake, that's exactly what a Boltzmann brane would think. If you point to the cosmic microwave background as proof of a real past, that evidence would be part of the illusion too. The only escape is to accept that reality, at its core, might be a self-solving riddle. A universe that exists because a momentary flicker of awareness convinced itself it must. So the next time you question your own existence, consider this. You might not be the observer of the universe, but the reason it appears observed at all. Deep in the fiery plasma of the early universe, particles existed that we've never seen and may never see again. Magnetic monopoles, hypothetical relics from the grand unification epoch, are the ultimate cosmic unicorns, solitary north or south magnetic poles, unlike anything in our current reality where magnets always come in pairs. But what if these elusive particles weren't just curiosities? What if they were the tiny matchsticks that lit the fuse of existence? Picture the universe a trillionth of a second after its birth, when the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were still merged into a single, perfect symmetry. As the cosmos expanded and cooled, that symmetry shattered like glass, fracturing into the distinct forces we know today. But symmetry breaks aren't always clean. Just as ice crystallizing on a pond leaves cracks and bubbles, the grand unification phase transition could have spawned topological defects, knots of trapped energy that refuse to smooth out. Enter magnetic monopoles, cosmic knots of pure magnetic charge, each one a billion times more massive than a proton. Now, here's where things get explosive. Monopoles aren't just heavy, they're cosmically catalytic. Their immense mass warps spacetime so intensely, they create zones where the vacuum's energy barriers thin to nothing. Imagine a bowling ball placed on a trampoline. The indentation it creates makes it easier for a marble to roll toward the center. Similarly, a monopole's gravitational grip could lower the energy required for quantum tunneling in its immediate vicinity, turning a statistical improbability into a near certainty. But the real fireworks start when monopoles interact with false vacuum. In quantum field theory, a false vacuum is a high-energy state that's stable but only temporarily, like a match balanced on its head. Given the right nudge, it can tunnel into a lower-energy, true vacuum, releasing a firestorm of latent energy in the process. Monopoles might have been that nudge. As they plowed through the early universe's plasma, their absurdly strong magnetic fields could have twisted quantum fields into pretzels, creating points of instability where false vacuum decay became inevitable. The math behind this is breathtaking. Calculations show that in regions surrounding a monopole, the energy barrier separating false vacuum from true vacuum could drop by orders of magnitude. Once one patch of spacetime tunneled, the released energy would trigger a chain reaction, a cosmic domino effect where each decaying region catalyzed its neighbors. The result, an exponential explosion of vacuum energy, inflating the universe faster than light itself could keep up. It's as if the monopoles were needles popping bubbles in cosmic bubble wrap, each pop unleashing a shockwave that reshaped reality itself. The echoes of this apocalyptic nursery rhyme might still linger today. If monopoles catalyzed vacuum decay, their remnants, those that survived the initial onslaught, could be floating through the cosmos right now, their faint magnetic signatures detectable with sensitive enough instruments. Some theorists even suggest that the mysterious cosmic rays bombarding Earth from deep space might carry traces of these ancient wrecking balls, whispers from the moment they helped rewrite the laws of physics. But the most haunting implication isn't about the past, it's about the future. If monopoles could catalyze vacuum decay once, could they do it again? Some models suggest that if even one rogue monopole survived to the present day and encountered a metastable patch of spacetime, it might trigger another catastrophic phase transition, a bubble of true vacuum expanding at light speed, rewriting the universe's laws as it goes. The good news, monopoles are theorized to be absurdly rare in our current epoch. The bad news, in an infinite multiverse, rare doesn't mean never. So the next time you hold a magnet in your hand, marvel at its twin poles, and remember that somewhere out there, a solitary cosmic wanderer might still drift, carrying with it the power to undo reality with a single quantum sneeze. What if the universe's first quantum leap wasn't just a jump through space or time, but a jump through math itself? This is the mind-bending premise of non-commutative geometry, a radical framework where spacetime didn't start as the smooth, predictable stage we know today, but as a chaotic quantum algebra where left and right didn't commute, where multiplying A by B didn't equal B by A. In this bizarre pre-geometric realm, the very concept of here and there would have been fluid, distances meaningless, and causality up for grabs. Then, in a single quantum tunnel, this wild mathematical landscape crystallized into the orderly, commutative geometry we now call reality. To grasp how profound this shift would have been, imagine trying to navigate a city where the order of your turns completely changes your destination. Take 2 steps forward, then 3 steps left, and you're at a cafe. but reverse the sequence 3 steps left first, then 2 steps forward, and instead of a latte, you're suddenly at the bottom of the ocean. That's the essence of non-commutativity. The sequence of operations isn't just important, it rewrites the rules of the game entirely. In the early universe, this could have meant that space-time itself was an ever-shifting puzzle, where quantum fluctuations didn't just tweak positions, but redefined the very axis of existence with every interaction. The breakthrough came when mathematicians like Elaine Connes realized that beneath this apparent chaos, non-commutative geometry isn't lawless, it's governed by spectral symmetries, hidden patterns that dictate how quantum observables relate. Think of it like a scrambled radio signal. To the untrained ear, it's noise, but with the right mathematical filter, a coherent broadcast emerges. In the pre-universe, these spectral rules might have acted as a hidden scaffolding, quietly guiding the quantum tumult until, through a tunneling event, the system snapped into a commutative phase, locking in the familiar rules of spacetime we take for granted. What's astonishing is how neatly this explains some of cosmology's deepest puzzles. The universe's eerie uniformity, the fact that distant regions share the same temperature despite never being in contact, might not require inflation's rapid stretching if those regions were never truly separate to begin with. In a non-commutative framework, locality is an illusion. Everything is fundamentally entangled at the algebraic level. Even the arrow of time could emerge from this transition, like a deck of cards shuffling from chaos to order, where the act of tunneling freezes one preferred sequence into permanence. The echoes of this geometric revolution might still linger today. If spacetime was born from algebra, then at the smallest scales, Planck lengths where quantum gravity reigns, we might detect residual non-commutativity like glitches in the cosmic matrix. Some theories even suggest that black hole singularities, where spacetime curvature runs amok, are places where the universe's original algebraic rules briefly resurface, poking holes in the commutativity we've grown used to. This isn't just abstract noodling, it's testable physics. Quantum gravity experiments aiming to probe spacetime's granularity could uncover signatures of non-commutative residue, like minuscule violations of Lorentz symmetry or energy-dependent light speed variations. Even the search for quantum memory effects in empty space hints that the vacuum remembers past interactions, could point to a deeper pre-geometric past. So the next time you measure the distance between 2 points, consider this. The ruler in your hands might be the descendant of a quantum mathematical revolution, a fleeting moment when the universe's equations simplified just enough to let reality take shape. The cosmos didn't just tunnel through energy barriers, it tunneled through the very rules of its own existence, emerging on the other side as a place where here and there finally made sense. The universe might owe its existence to a cosmic game of hide and seek, one where reality itself was trapped by the very act of being observed. This is the bizarre paradox at the heart of the quantum Zeno effect, a phenomenon where constant measurement can freeze a system in place like a butterfly pinned under glass. Normally, particles flicker between states. Think of radioactive decay, where atoms unpredictably shed energy, but bombard that atom with relentless observations and something strange happens, it never decays. The quantum Zeno effect acts like a cosmic pause button, where watching something too closely stops it from changing at all. Now stretch this idea to the scale of cosmic origins. What if the pre-universe void wasn't empty but stuck, trapped in a timeless stasis by relentless quantum observations from an underlying field or interaction we can't yet fathom? Picture a room filled with motion detectors, each one primed to snap a photo the moment anything moves. Now imagine a single particle trying to drift from one side to the other. Every time it twitches, a detector fires, resetting its position. The result, the particle never gets anywhere, it's perpetually frozen mid-motion. In the pre-universe, this could have been the default state. quantum fields so entangled with their own self-interactions that every fledgling fluctuation was instantly measured and snuffed out before it could grow. Space, time, even causality would have been locked in perfect paralysis, like a record needle trapped in an infinite groove, but quantum mechanics has an escape clause. No observation is perfect, no freeze permanent, given enough time, or more accurately, outside the arrow of time entirely, a statistical fluke would inevitably slip through the cracks. One quantum fluctuation might evade the cosmic surveillance, tunneling through the Zeno trap before the next measurement could reset it. Think of it like a prisoner timing the guard's patrols. If the gap between observations is just wide enough, reality gets a head start, ballooning outward faster than the freeze can reclaim it. The math behind this is both counterintuitive and elegant. The quantum Zeno effect relies on wave function collapse, the idea that observation forces quantum possibilities to choose a state. In the pre-universe context, this collapse wouldn't require conscious observers, but natural interactions acting as pseudo-measurements. Calculations show that the more frequent these interactions, the slower the system evolves, a principle called the watchdog effect. But crucially, there's always a finite probability, however small, that a fluctuation will tunnel out unnoticed. When that happens, the payoff is cosmic. The escaped fluctuation doesn't just fade, it inflates, stretching into an entire universe while the Zeno effect's grip shatters behind it like broken glass. Supporters of this theory point to eerie parallels in lab experiments. Ultra-cold atoms confined by laser observation have been shown to resist decay exactly as the quantum Zeno effect predicts. Even more compelling, certain quantum gravity models suggest spacetime itself might emerge from similar watchdog processes at Planck scales. If true, our universe's birth wasn't just an accident, it was a prison break, a single fluctuation that outran the cosmic warden long enough to become everything. So the next time you glance at the stars, consider this. The very act of looking might be a fleeting defiance of the quantum rules that once sought to lock reality away forever. Black holes aren't just cosmic vacuum cleaners, they might be cosmic printers, encoding everything they swallow into quantum radiation so fine-tuned, it births entire universes. This is the radical idea behind the information-theoretic singularity theory, where the resolution to physics' greatest paradox hinges on quantum tunneling of the most poetic kind. At its core lies the black hole information paradox, a puzzle so profound, even Stephen Hawking wrestled with it for decades. According to quantum mechanics, information can never be truly lost. Every atom, every photon carries data that should, in theory, be recoverable. But black holes defy this. When matter falls in, it vanishes behind an event horizon, seemingly erased from existence. Hawking's own calculations suggested these cosmic traps weren't just dark, they glowed faintly with thermal radiation, slowly evaporating over eons. But here's the catch, that radiation appeared random, carrying no trace of the original matter that fell in. Like burning a library and claiming the smoke carries the words from every book. Enter quantum tunneling. If information can't be destroyed and it isn't in the Hawking radiation, then perhaps it doesn't stay in our universe at all. Some physicists propose that when a black hole forms, the collapsed matter doesn't just squeeze into a singularity, it tunnels through a quantum loophole, emerging as the seed of a brand new cosmos. Think of it like a cosmic game of telephone where the message isn't lost, just whispered into another reality's ear. In this scenario, Hawking radiation isn't random noise, it's the afterglow of that tunneling event, the thermal exhaust from a universe being born in the darkness. The math behind this is as elegant as it is mind-bending. Black hole thermodynamics treats entropy not as disorder, but as hidden information, bits encoded on the event horizon's surface like a hologram. When matter falls in, those bits rearrange, preserving the data in scrambled form. But if the interior tunnels into a new space-time, that information isn't lost, it's simply transferred like files moved to a different hard drive. This solves the paradox by making the black hole a bridge rather than a blender. Even more astonishingly, the new universe's physical constants could be shaped by the parent black hole's quantum states, meaning every singularity might spawn a reality with subtly different laws. Supporters of this theory point to eerie symmetries. The universe's low initial entropy, a prerequisite for time's arrow, aligns perfectly with a black hole's high entropy collapse, as if our cosmos inherited its order from a previous one's chaos. Even dark energy finds an explanation. It could be the residual tension from that primordial tunneling event, like stretch marks in spacetime itself. Critics argue we'll never observe these daughter universes, but proponents counter that their existence isn't just speculative. It's necessary to preserve quantum mechanics' most sacred rule: information never dies. It just changes address, so the next time you gaze at the night sky, consider this. The black holes silently spinning in the darkness might not be endings at all, but cosmic wombs, weaving the fabric of new realities from the quantum static of their own dissolution. Imagine a geometric language so alien, it defies visualization, a mathematical realm where numbers don't just describe dimensions, but twist them into shapes that evaporate if you stare too long. This is the world of octonions, the largest and strangest of the normed division algebras, where multiplication isn't just non-commutative, it forgets to be associative too. In simpler terms, even the order of operations loses its grip here. Now picture the pre-universe as a frothing sea of these octonionic geometries, each a fleeting pattern in the quantum foam, flickering between existence and oblivion. According to this theory, the cosmos didn't just tunnel through energy barriers. It tunneled through mathematics itself, leaping from one exceptional geometry to another like a cosmic dancer pirouetting between impossible angles. At the heart of this idea lies the exceptional Jordan algebra, a mathematical structure built from octonions that describes symmetries too elegant for ordinary spacetime. These symmetries aren't just abstract, they're the hidden scaffolding of reality, governing how quantum fields interact at energies so high they only existed during the universe's first trembling moments. Under these conditions, octonionic geometry wouldn't just influence physics, it would be physics, with every particle and force emerging as vibrations in its hyperdimensional lattice. The catch: octonionic systems are notoriously unstable. Their mathematical beauty is razor-thin, balanced on a knife's edge where the slightest perturbation collapses the whole delicate structure. That's where quantum tunneling comes in. In the pre-universe chaos, fluctuations in the octonionic field could have nudged the system toward a critical threshold, a point where the algebra's inherent instability became its salvation. Like a Rube Goldberg machine teetering on the verge of motion, one quantum jump could have triggered a cascade, tunneling the entire system from an octonionic geometry into the more stable quaternionic framework that underlies our familiar four-dimensional spacetime. Think of it as a cosmic phase transition, but instead of water freezing into ice, it's mathematics crystallizing into reality. The implications are staggering. If octonionic geometry guided the tunneling event, it could explain why our universe has exactly four fundamental forces. Each one corresponds to a remnant of the octonion's broken symmetry. Even the seemingly arbitrary strengths of those forces might be fossils of this primordial mathematical collapse. String theorists have long suspected octonions lurk in M-theory's deepest layers, and some formulations of quantum gravity suggest spacetime's very dimensionality. Why we experience 3 dimensions of space and 1 of time could be the fallout of this algebraic descent. Critics argue that octonions are too abstract to test, but supporters point to eerie experimental hints. The exceptional Lie group E8, which governs octonionic symmetries, has been spotted in the energy spectra of certain quantum materials. Meanwhile, anomalies in high-energy particle collisions occasionally match predictions from octonionic models, as if we're catching glimpses of a deeper geometry bleeding through. Even dark matter's gravitational fingerprints could be shadows of octonionic structures, hidden dimensions folded so tightly they only interact via gravity's faintest whisper. So the next time you solve a simple equation, remember, the numbers on your page might be the pale echoes of a far stranger arithmetic one that didn't just describe the universe's birth, but was it? Time doesn't just pass, it thaws. This is the startling revelation at the heart of the thermal time hypothesis, a radical reimagining of time's arrow where the steady tick of the cosmos isn't an intrinsic feature of reality, but the emergent shudder of a universe cooling from its first quantum jump. Picture the newborn cosmos not as a static void, but as a superheated forge where temperatures were so extreme they blurred the line between time and energy. Here, in this primal inferno, quantum tunneling didn't just create particles. It carved the very channels through which time would flow, like meltwater tracing fissures in ice. The thermal time hypothesis, pioneered by Elaine Connes and Carlo Rovelli, flips traditional physics on its head. Instead of treating time as a fundamental backdrop against which events unfold, it suggests time is a side effect of thermodynamics, a shadow cast by the universe's relentless drive toward equilibrium. In this framework, the flow of time isn't baked into spacetime's fabric. It emerges from the statistical dance of quantum states as they tunnel toward lower energy configurations. Think of it like a film reel. What we perceive as the smooth passage of time is really just a sequence of quantum snapshots, each frame a new tunneling event lowering the system's overall temperature. At the Big Bang, this process would have been electrifyingly dramatic. The universe's initial state, a seething, maximum entropy chaos, wasn't just hot. It was timeless, a quantum soup where cause and effect swirled indistinctly. But as the first particles tunneled into existence, they didn't merely pop into being, they introduced the faintest thermal gradient, a microscopic temperature difference that acted like a cosmic compass needle, pointing the way from before to after. It's as if the universe's first quantum leaps didn't just fill space with matter, but with the very directionality of time itself. The math behind this is as elegant as it is counterintuitive. In Connes' non-commutative geometry, time arises from the algebra of quantum observables, a kind of cosmic ledger tracking how systems evolve. Rovelli's loop quantum gravity then ties this to thermodynamics, showing how quantum tunneling events generate entropy gradients that break temporal symmetry. Translated into everyday terms, every time a particle tunneled through an energy barrier in the early universe, it didn't just change its own state. It contributed to a vast, irreversible thermal drift, like a single snowflake tipping an avalanche. What makes this idea so compelling is how neatly it solves one of physics' oldest puzzles. Why time only moves forward? The answer, it doesn't, not fundamentally. The arrow of time is just the universe's memory of its own cooling, a fossil record of quantum tunnels leading from hot to cold, from chaos to order. The echoes of this process might still resonate today. Black holes, with their infinite time dilation at the event horizon, could be windows into a pre-thermal reality where time's arrow flickers and fades. Even quantum computers, which exploit superposition to perform calculations outside classical time, might be tapping into the same primordial timelessness that preceded the Big Bang. Critics argue that thermal time reduces causality to a statistical fluke, but supporters counter with an eerie observation. The cosmic microwave background's near-perfect uniformity suggests the early universe was in thermal equilibrium, a state without time's flow. Only as quantum tunneling broke that symmetry did time's arrow crystallize, pointing the way toward the structured cosmos we know. So the next time you check your watch, remember, you're not just measuring hours and minutes, but the faint afterglow of the universe's first and greatest escape, a quantum leap that didn't just create matter, but the very stage on which its story unfolds. From black holes birthing universes to consciousness collapsing reality, the theories we've explored today stretch the limits of imagination, yet they all share one extraordinary thread. quantum tunneling as the universe's ultimate escape artist. Whether it's cosmic strings prying open reality seams, phantom energy rewriting the rules of existence, or even time itself emerging from mathematical chaos, these ideas reveal how deeply physics and philosophy intertwine at the edge of understanding. Each theory is a different lens on the same cosmic mystery, proving that the birth of reality might be stranger than any fiction. Some explanations feel like pure mathematics, like octanenic geometry crystallizing into space-time or Chern-Simons equations weaving existence from abstract knots. Others read like cosmic poetry, Boltzmann brains dreaming up stars, or entangled universes whispering into being through quantum threads. And then there are the visceral, almost apocalyptic visions, monopoles detonating false vacuums, colliding brains igniting firestorms of creation. What unites them all is the audacious idea that existence itself could be a quantum loophole, a momentary flicker that shouldn't have been possible, but was. As we stand at the crossroads of these ideas, it's worth asking, which theory sparks that tingle of recognition for you? Does the elegance of holographic emergence pull you in, or does the rawness of Planck stars and black hole rebounds feel more compelling? Maybe the answer changes depending on the day. That's the beauty of cosmology. It's not just about finding answers, but about learning which questions captivate us most. After all, the universe's first quantum leap might remain a mystery for centuries to come, but the act of wrestling with these possibilities, that's where the real magic happens. So hit pause, let your imagination roam, and drop your favorite theory in the comments below. Was it the cosmic hologram, the timeless bounce, or something we didn't even cover today? And if you love diving down these rabbit holes with us, don't forget to subscribe, because the universe's secrets aren't done unfolding, and neither are we. Until next time, keep looking up and wondering what might lie beyond, beneath, or even before the stars.